Hi everybody, this is Rich, and today I'm here to tell you about an engine. Several months ago I made a quick and dirty video about the HOTOL project. This was a project by British Aerospace and Rolls-Royce to build a fully reusable space shuttle. The video is just me talking over a bunch of old slides, but somehow this has been my most popular video to date. There's clearly a lot of interest around this topic, and there's a terrible shortage of good information, so I thought another video was definitely in order. HOTOL occupies a very interesting place in space history. The technology developed for it is unique and potentially revolutionary, even now. But at the same time, few people outside the United Kingdom seem to have heard of HOTOL, and even amongst those who have heard of it, there is very little understanding of how it would have worked and why it was so special. If you show a picture of HOTOL to an American space fan, you'll probably hear, "Oh, another rocket plane. We tried those and they're not very good." Occasionally you'll get a shrug and a question whether it uses scramjets. If you want to know why HOTOL was different, what you really need to understand is the engine, which wasn't a scramjet. Back in the 80s when the project was going on, there was actually very little information available to the public. A lot of this was because the engine technology was classified by the UK government. In the present day, that isn't a problem. In fact, if you want, you can download a copy of the patent that explains how the engine works. Patents can be quite long-winded and difficult to understand without specific engineering knowledge and context. What I'm going to do, with the aid of some diagrams that I've drawn, is explain the core principles. From that perspective, the engine's actually pretty simple to understand, once you know what's going on. First though, a bit of context. Access to space is very expensive, and the main costs of this are expendable launch vehicles, rockets that are only designed to be used once, and the fact that rockets tend to be in multiple stages. The ideal launch vehicle, therefore, is not just one that you can use again, but also one that comes as a single vehicle. But the rocket equation is brutal. If we have to achieve an orbital velocity of 8.5 km per second, and our exhaust velocity is 4.5 km per second, the mass fraction that this allows us is not possible with current technology. Indeed, Alan Bond, the inventor of the HOTOL engine, is known to say that the Earth is just 10% too big. If it was just a little bit smaller, then the rocket engines that we have would be good enough to reach orbit in a single stage. As it is, the only way we can make the numbers add up is to fly a rocket off the top of another rocket. A lot of work has been put into fully reusable single-stage to orbit vehicles, particularly in the United States. These concepts tend to revolve around a lot of exotic new technologies. So, for example, ultra-light composite fuel tanks, aerospike engines, scramjets, that sort of thing. Inevitably, what happens is that the cost of developing these projects spirals over time, with the result being that the projects get cancelled, and a belief develops that single stage to orbit is not only insanely expensive, but impossible to achieve. From the beginning, the designers of HOTOL adopted a totally different approach. As much as possible, it had to use simple, well-established technology. So, for example, British Aerospace could draw on their experience with Concorde to design the airframe. Likewise, Rolls-Royce had experience with rocket engines, including the RZ-2, which was on the Blue Streak missile, and the RZ-20, which was never finished but is significant because it was a hydrogen-oxygen engine. The first insight that led towards HOTOL was the understanding that such engines are almost good enough, and all they need is a little bit of assistance. This wasn't new with HOTOL, and several concepts had looked at this, the most interesting being the American Star Raker concept. Orbital speed is the equivalent of about Mach 25, or 25 times the speed of sound, and a launch vehicle is effectively a dragster that starts at zero and has to reach this speed. If we make assumptions for existing materials and engine performance, we can work out how much that rocket can achieve, and then see how big the shortfall is. If we make reasonable assumptions, the answer's pretty clear. Single stage to orbit works just fine if you can launch when you're already travelling at a speed of Mach 5, and you're at an altitude of 25 kilometers. The obvious solution, which frees us from the rocket equation, is to use some kind of air-breathing engine. The problem is, though, that jet engines won't even get you to Mach 3, let alone to Mach 5. So designs inevitably end up taking off on jet engines, accelerating through the speed of sound using afterburners, switching over to ramjets at about Mach 2.5, and then maybe even to scramjets before finally the rocket takes over. This is being called the Smithsonian to orbit method, so called because it has one of everything. The problem is how much it all weighs. Remember, engines are just dead weight when they're not being used. The key insight behind HOTOL was to forget adding additional engines, and instead to modify the rocket engines to do both jobs. Could the rocket engine be made to suck in air and burn it with the hydrogen in place of the liquid oxygen, just for the first part of the ascent? It wouldn't even need to be particularly efficient as long as it was light. Of course the answer is yes, and the secret of how it could do this is all down to the remarkable properties of liquid hydrogen. But we're getting ahead of ourselves. So, to explain how this engine works, let's go back to basics. What we want to do is we want to take our reaction mass and throw it as hard as we can backwards from the vehicle. In terms of physics, what we're doing is doing work on that mass. We're accelerating it from a standing start to some velocity. If we're dealing with a gas, one thing we can do is pressurize it and then pass it through a nozzle. This causes the gas to accelerate as it flows from high pressure to low pressure. The next question is how we pressurize the gas. We could do the work to pressurize the gas all in one go before we launch the rocket, just like blowing up a balloon. The problem with this is that the storage tank would be extremely heavy. Instead, what we have to do is store the gas at low pressure and then pressurize it as we go along. To do that, we need a lot of power, and that's why we're talking about a rocket engine. Specifically, we use something called a heat engine. You may not have heard of heat engines, but I guarantee that you use one every day. There's one keeping your lights on, for example, and there's one in your car. A heat engine is a device that converts heat into mechanical energy. For a rocket engine, and indeed a jet engine, the process is the same. The cold working fluid enters the engine, and it's compressed by a compressor or a pump. The fluid, now at high pressure, is then heated. The hot fluid is then expanded again through a turbine, and the mechanical work from the turbine drives the compressor or pump. The reason we do this is that the mechanical work required to compress a cold fluid is significantly less than the amount of mechanical work required to compress a hot fluid. That means that if the turbine is just big enough to drive the compressor or pump, the pressure of the fluid leaving the turbine will be significantly higher than the pressure of the fluid entering the engine. Or to put it another way, this engine uses heat to do mechanical work on the fluid passing through it. The nozzle then uses that work to eject the fluid at speed. This process is something that's called a thermodynamic cycle, and whilst that might sound intimidating, remember that in essence it's the same as what's going on in your car engine. Induction, compression, ignition, expansion. Or indeed suck, squeeze, bang, blow, as we used to snigger about as teenagers. In theory, we can keep increasing the power of the engine by adding more heat. In the real world, however, we're actually limited by the materials that we can build the turbine out of. What we can do, however, is we can introduce heat to the system downstream of the turbine. We can reheat the fluid. Increasing the temperature of the flow through the nozzle increases the amount of mechanical energy released, and this increases the exhaust velocity, giving us more thrust. We have a name for this in a jet engine, of course. We call it an afterburner. In a rocket engine, however, this is simply called the main combustion chamber. The main difference between a rocket and a jet, of course, is that in a jet the majority of the working fluid comes from the atmosphere. In a rocket, all of the working fluid comes from internal tanks. The reason I've presented both as the same concept here is that in HOTOL we start to blur the boundary between rocket and jet. As I've shown already, in a single stage-to-orbit vehicle what we care about most is a high-efficiency rocket engine. The rocket does do 80% of the acceleration after all. So for the moment, let's just consider a pure-breed rocket, and we can add the air-breathing part in later. This is the same cycle that we were just looking at, but with two fluids instead of just one. There are many ways of adding heat to a cycle, including nuclear reactors or electrical resistance, but for the most part what we use is combustion. We combine two fluids and ignite them. This cycle is called the staged combustion cycle, and it's the one that was most famously used in the Space Shuttle main engines, albeit with a few nuances that I've kept out here to keep things simple. In this cycle, our turbine drives two pumps, one for liquid hydrogen and one for liquid oxygen. We then bring these two fluids together and ignite them where we want heat. In this layout, as with the Space Shuttle, the hydrogen is the main flow, and oxygen is added, but there are other engines where the oxidizer is the main flow, for example the Soviet NK-33. As the name would suggest, in this cycle the combustion happens in stages. In order to power the turbine, we mix some of the oxygen with the hydrogen in a preburner. How much we can add here is dependent on the maximum operating temperature of the turbine. These combustion products, essentially hot hydrogen and steam, pass through the turbine and then onto the main combustion chamber via the injector. In the combustion chamber, the remaining hydrogen and oxygen mix and release a large amount of heat. The hot, high-pressure combustion products then expand out of a nozzle, creating thrust. There is an extra nuance to this cycle that's worth mentioning at this point. The temperatures inside the combustion chamber are far higher than the melting point of any material that could be used to build it. These surfaces therefore need to be actively cooled to prevent them from disintegrating. The most common solution is to employ the fuel as a coolant. By passing the pressurized liquid hydrogen through small channels built into the nozzle and the combustion chamber, it's possible to absorb the heat that's building up in the walls, keeping them at an acceptable temperature. There's also a second benefit to this. Using the hydrogen as a coolant also preheats the hydrogen before it enters the preburner, meaning that less combustion has to occur there. In thermodynamics, this process of taking heat from the exhaust and putting it back into the engine has a name. It's called regeneration, and that's why we call this regenerative cooling. That then is the staged combustion cycle. As I said, it was used in the Space Shuttle main engine, which was some of the best performing rocket engines ever built. So where do we go from here? Can we improve on this if we're going to build a spaceplane? I can already hear the SpaceX fans jumping up and down in the audience shouting, "Full flow staged combustion." Well, I'm going to disappoint you guys because there's a way that we can improve on this engine without adding all of that extra complexity, and this is the route that the HOTOL engine designers went down. It turns out that if we can absorb enough heat into the hydrogen through regenerative cooling, we can do away with the preburner entirely. And to paraphrase Elon Musk, the best component is no component. It can't fail and it doesn't cost anything. This leaves us with something called an expander cycle rocket engine. These are nice engines because they're simple. There are fewer parts, so they're lighter and there's less to go wrong. They're also capable of very high performance. They can achieve similar exhaust velocities to a staged combustion engine. So what's the catch? The biggest drawback to an expander cycle engine is that they are thrust limited, which is just a fancy way of saying you can't build them above a certain size. They fall victim to something called the square-cube law, specifically the relationship between the volume of the combustion chamber and nozzle and the surface area. Think of it like this. If we look at the engine end-on, the amount of heat captured by the engine depends on the perimeter of the nozzle, whereas the amount of mass flow through the engine depends on the area. If we build a rocket engine double the size, we will have double the perimeter, so we can achieve double the heat transfer. However, the amount of propellant flowing through the engine will have increased with the area, which will have increased by a factor of 4. So that's half as much heat for each unit of propellant. This is why expander cycle engines tend to be upper stage engines, where efficiency is more important than high thrust. Examples include the American RL-10, which is used in the Centaur upper stage, or the European Space Agency's Vinci, which is intended for use in Ariane 6. Whilst a sea-level version of the RL-10 was in fact used on the DC-X, expander cycle engines are totally unsuitable to the first stage of large vertical launch rockets, where large amounts of thrust are essential to getting off the pad. Of course, with a single stage-to-orbit spaceplane, the rocket mode is in effect the upper stage. What we need is a simple, lightweight, high-efficiency engine, which makes an expander cycle a suitable candidate. So how is the HOTOL engine different from a normal expander cycle? Looking at the patent, the first thing that we see is an innovation that would allow an expander cycle engine to be built at any size. You could almost call it a staged combustion expander cycle. In this modified cycle, the combustion chamber is extended, and there are 2 sets of injectors. Between the injectors, in the space that you could call the preburner or pre-combustion chamber, there's a heat exchanger. The heat exchanger would probably take the form of a large number of small tubes, carrying the hydrogen across the hot gas flow. What this does is solve the surface area problem we described earlier. The total surface area of the tubes will be a heck of a lot larger than that of the surface area of the nozzle. So it's possible to heat very large flows of hydrogen, which will come in useful, as you'll see in a moment. Just like in the staged combustion cycle, 2 injectors are used so that the temperature in the preburner can be controlled. This ensures that the heat exchanger tubes don't get too hot, and also makes it possible to control the hydrogen temperature going into the turbine. This in itself is quite a neat arrangement, but what it's doing is setting us up for what we do next, which is introduce the air-breathing part of the engine, and this is where HOTOL represents something truly revolutionary. As we've said before, our air-breathing spaceplane needs to be able to reach speeds of at least Mach 5 before switching over to a pure rocket. Operating below Mach 5 then, we need to be able to capture air and then compress it so that we can put it into the rocket combustion chamber. This is difficult, because when air enters a supersonic air intake and gets slowed down into the engine, its kinetic energy is converted into heat. By the time the spaceplane reaches Mach 5, the temperature of the air reaching the compressor will be over 1000 degrees Celsius. There are two big problems with this. The first is that no compressor can deal with that kind of temperature, and the second is that hot gases require a huge amount of energy to compress. Remember our heat engine from earlier on. We expanded hot gas and used that to compress cold gas, and we had some power left over. If the air entering our spaceplane's compressor was cold, it would require a lot less power to compress it. The stroke of genius that led to HOTOL was the idea to use the hydrogen fuel as a coolant to cool the air. Hydrogen is an incredible coolant. It's about 4 times better than water, and it's being stored in the vehicle's fuel tanks at temperatures of about 15 degrees Kelvin. So here's what the HOTOL engine air breathing mode looks like. The air from the vehicle's air intakes, as it enters the engine, passes through a heat exchanger. This heat exchanger uses cryogenic liquid hydrogen to cool the air down to a temperature just above its liquefaction point, around minus 180 degrees Celsius. This heat exchanger is sometimes called a pre-cooler, because it pre-cools the air just before it enters the compressor. At this low starting temperature, it's actually relatively easy now to compress the air to a high delivery pressure of several hundred bar and to put it into the rocket combustion chamber. Now, in this engine, the hydrogen actually performs two functions. It's the fuel, but it also serves as a coolant. When you sit down and work out just how much heat can be absorbed by a certain amount of hydrogen, what you soon discover is that the amount of hydrogen flow required to cool the air to the desired temperature is actually more than twice what you need to burn it stoichiometrically in the combustion chamber. Stoichiometric, of course, meaning that there are 2 hydrogen atoms for every oxygen atom entering the combustion chamber. So we have a lot of excess high temperature, high pressure hydrogen that we can't burn in the engine. So what happens in this design is that half of the hydrogen goes to the combustion chamber, and the other half is expanded through a turbine that drives the air compressor. It's then dumped overboard. This might seem like a terrible waste of reaction mass, but it's just a tiny fraction of the mass of air that it allows the vehicle to capture. The patent actually quantifies these benefits by including a graph showing the engine efficiency at various Mach numbers. It follows a rather sensible quirk by British rocket engineers to show specific impulse as an effective exhaust velocity. To the Kerbal Space Program SpaceX generation, however, I think this might be better understood if we arbitrarily divide it by 9.81 meters per second squared and arrive at a number expressed in seconds. The specific impulse of HOTOL's engine in air-breathing mode is estimated to be between 14 and 2300 seconds, depending on the vehicle's speed in the atmosphere. To give you an idea how this fuel efficiency compares with high-performance pure rockets, the specific impulse of the Space Shuttle main engine at sea level was only 366 seconds. The SpaceX Raptor comes in even lower, at 330 seconds, although that's burning methane rather than hydrogen. You can think of this as a comparison of the performance of the first stage of a rocket, and for a pure rocket why the first stage has to be enormous and discarded after use. HOTOL is 4 to 6.5 times more fuel efficient, and that has a huge impact on the vehicle design. Think of it like a reverse snowball. A lot less fuel is required, the structure can be lighter, and the engines can be smaller, so a lot less fuel is required, and so on. You end up with a first stage so small you can carry it with you into orbit. Getting to around Mach 5 is just the first fifth of the acceleration required to get to orbital speed. For the rest, what's required is a high-efficiency pure rocket engine. This is where the HOTOL engine comfortably reverts to being an expander cycle engine. The hydrogen flow drops down to normal levels, and power to the air compressor is shut down by means of a valve cutting off the flow of hydrogen to its turbine. The flow of compressed air to the combustion chamber is replaced by liquid oxygen, delivered via a turbopump. The big advantage to this, of course, is that no second set of engines is required. The amount of dead weight that would have to be hauled into orbit and back is much reduced. Operating as an expander cycle engine, we could expect the HOTOL engine to have a typical performance of around 450 seconds in vacuum. This is comparable to the Space Shuttle main engine, and other engines like the Vinci and the RL-10. These then are simplified diagrams of the HOTOL engine's cycle. Like any rocket engine, there are more details to the cycle when you look closer. So for example, how the engine copes with different intake air temperatures at different Mach numbers. If you're interested, I highly recommend taking a look at the patent. I'm going to finish though by mentioning two issues with the engine that aren't mentioned in the patent, but anybody building this engine would have to contend with. The first issue is something called frost control. We've already mentioned that the air entering this engine is cooled down to just above the liquefaction point of air. The problem is that air, particularly at low altitude, contains water vapour. The researchers on HOTOL found that this would freeze into ice that would block the heat exchanger matrix in a matter of seconds. This problem was actually solved years later by researchers at a company called Reaction Engines, which was set up to continue researching HOTOL technologies after the project was cancelled. According to their patent, the system works by introducing a methanol antifreeze into the airflow, which allows them to capture the water as a liquid. The other technical challenge with this engine is something called altitude compensation. The best shape for a rocket engine is dependent on the ambient pressure that it's operating in. Engines that are optimised to work in a vacuum, like for example the ones on the Space Shuttle, suffer a performance penalty if they operate in an atmosphere. The usual solution to this is to use different engines on the first and second stage, but for HOTOL this isn't an option. The patent doesn't make it clear how this problem would have been addressed. It's unlikely that aerospike nozzles would have been chosen on the basis that the technology is A more likely solution is something like a dual bell nozzle, or maybe an expansion deflection nozzle. None of these technologies are depicted in any of the HOTOL artwork, of course. So there you have it. That's how the HOTOL engine would have worked. It was actually a relatively simple piece of technology, almost certainly easier to build than something like the SpaceX Raptor, which is a technological marvel. I think that the undoing of this engine has been the fact that the original simple engine seen here was classified top secret by the UK government, forcing its inventor to develop a different, better engine at the expense of a significant increase in complexity. If the original, simple engine had been subject to a technology development program similar to that employed by SpaceX, things might well have turned out differently. And they might yet. I don't think that we've seen the last of these engines.